All right, hello everyone. I apologize first of all for getting this up later than normal. Life sort of got in the way as it usually does. So last week we talked about special relativity. We talked about space and time. Tonight we're going to talk about Einstein's theory of general relativity, in that case, just space-time and gravity. Tonight's quote is, of course, from the man of the hour, Einstein. He said that the eternal mystery of the world is its comprehensibility. The fact that it is comprehensible is a miracle. So we're going to talk about general relativity tonight in very abstract terms. We're not going to do much math. There's going to be like 2 thought experiments as opposed to the 12 from last week. Hopefully this will be relatively understandable. So let's get started with this first little thing to help us understand this revolution in thinking. So let's imagine that you and everyone around you believe that Earth is flat. And hopefully you are a wealthy person and you're a patron of the sciences. And so you decide to sponsor an expedition to the far reaches of the world. You select 2 fearless explorers and give them careful instructions that each is to journey along a perfectly straight path, but they are to travel in opposite directions. You provide each with a caravan for land-based travel and a boat for water crossings, and you tell each to turn back only after discovering something extraordinary. Sometime later, the 2 explorers come back and you ask, did you discover something extraordinary? And to your surprise, they answer in unison, yes, but we both discovered the same thing. We ran into each other despite having traveled in opposite directions along perfectly straight paths. Now, hopefully this conclusion isn't that surprising to us in our real world because we know that the Earth is round. In a sense, these explorers follow the straightest possible paths, but these straight lines follow the curved surface of the Earth. So now let's consider a more modern scenario where you are floating freely in a spaceship somewhere out in space. Hoping to learn more about the space in your vicinity, you launch 2 small probes along straight paths in opposite directions, and each probe is equipped with a camera that transmits pictures back to your spaceship. So imagine that to your astonishment, the probes one day transmit pictures of each other back to you. That is, although you launch them in opposite directions and neither of them has ever fired its engines, the probes somehow met. This might at first sound surprising, but in fact, this situation arises naturally with orbiting objects. If you launch 2 probes in opposite directions from a space station, they will meet as they orbit the Earth. Now, since the time of Newton, we generally explain these curved paths, such as the ones by these 2 probes, as caused by the force of gravity. But in analogy with those explorers on the flat Earth, we might actually instead conclude that the probes meet because space is somehow curved. This idea lies at the heart of general relativity. And it's contained in that theory when Einstein published it in 1915. All right, one more thought experiment here. So let's imagine that you and Al are both floating weightlessly in your spaceships. That is, you are in free float reference frames. So as we saw last week, there's obviously no answer to the question, who is really moving, because you both will experience the laws of nature in the exact same way. But now, suppose that you decide to fire your rocket engines with enough thrust to give you an acceleration of 1g, that is 9.8 meters per second squared, which is the acceleration of gravity here on Earth. Al keeps his engines off and therefore sees you flying off with ever-growing speed, and so he quickly sends you a message saying, goodbye, have a nice trip, see you never. If all motion is relative, as we claimed last week, then you should be free to claim that you are still stationary and it is Al that is receding away into the distance. So therefore, you might reply, thanks, but I'm not going anywhere. You're the one leaving forever. However, this situation has an aspect to it that we haven't talked about last week, and I bet you can spot it. Here, we're dealing with acceleration. Because your rocket engines are firing, you feel a force inside your spaceship that means you will no longer be weightless. You have weight here. In fact, with an acceleration of 1g, you will weigh the same amount as you would weigh standing on Earth. So Al may then respond to your message, oh yeah, if you're not going anywhere, why are you stuck to the floor of your spaceship? And why do you have your engines turned on? And if I'm accelerating as you claim, why am I weightless? Now, we've got to admit, Al is asking some pretty good questions here. It certainly looks as if you are the one who is really accelerating while Al remains stationary. In other words, it seems that motion is no longer relative when we introduce acceleration, when we move away from constant velocities. And this idea is something that Einstein absolutely hated. He truly believed that all motion is relative, regardless of whether you're going at a constant velocity with no acceleration or you have a changing velocity with some acceleration. So Einstein needed some way to explain his way out of this weird little scenario. And he did it through what he called the happiest thought of his life, which he had in 1907. And his thought was that when you feel weight, you can attribute it to the effects of either acceleration or gravity. And this is known as the equivalence principle, where the effects of gravity are exactly equivalent to the effects of acceleration. So according to the the equivalence principle, if you were sitting inside a room with no doors, no windows, just like this poor man is doing here at the left, and then you were magically removed from Earth and sent hurtling through space with an acceleration of 1g, 9.8 meters per second squared, according to the equivalence principle, you would have no way of knowing that you left Earth. Any experiment you perform, such as dropping balls of different weights, would yield the same results that you got on Earth. So this equivalence principle actually gives us a way to answer Al's questions when he saw us blasting off into space. So he asked how you could be stationary when your engines are firing and you feel weight. You can now answer that space is filled with a gravitational field that points downward towards the floor of your spaceship. You are stationary because your rocket engines prevent you from falling through this gravitational field. And the gravity also gives you some weight. How do you answer Al's second question about his own weightlessness? Well, easy, because he's not using his engines. He and his spaceship are falling through this gravitational field that fills the space around you. And of course, as we learned many, many weeks ago, anyone in free fall will feel weightless. So in essence, you are claiming that the situation is much as it would have been if you were just hovering over a cliff here on Earth. So to summarize, you respond, sorry, Al, but I still say that you have it backward. I'm using my engines to keep myself from falling, and I feel weight because of gravity. Duh. You're weightless because you're in free fall. I hope you don't get hurt by whatever's at the bottom of this cliff. Good luck. So this equivalence principle is pretty much the starting point for general relativity. So as this little thought experiment is shown, it allows us to treat all motion as relative, just as Einstein believed we should be able to do. And this will lead to some pretty fundamental changes about how we view our universe. So, but it's sort of easy to say that we could attribute our weight to gravity or acceleration, but those two things look very different. A person standing on the surface of the Earth appears to be motionless, while an astronaut accelerating through space continually is gaining speed. So how can gravity and acceleration produce very similar effects when they look so different? And the answer to that question is that we're not really seeing the whole picture. Instead of looking just at the 3 dimensions of space, we've got to learn to look at the 4 dimensions of space-time. And so let's talk about, first of all, what I just mean by dimension. You probably already have a pretty conceptual idea of what dimension is, just from schooling, just from basic math class. But essentially, dimension is the number of independent directions in which movement is possible. So for example, a point has 0 dimensions. If you were a geometric prisoner sitting on a point, you could go nowhere. There's literally no direction that you can move. If you sweep a point back and forth, then you get a line, and line is 1-dimensional because you only go in one direction. Move that line back and forth, and you get a 2-dimensional plane, like a square or a circle, rectangle, triangle. We know these shapes. And so the 2 directions are, say, lengthwise and widthwise. Any other direction, such as diagonal, is just a combination of those 2. If you move a plane back and forth, then it fills up a 3-dimensional space. So it'll be cubes, spheres, triangular prisms, that kind of stuff, where we've got length, width, and depth now. And so we live in a 3-dimensional space, and we Literally, it is impossible for our human brains to imagine any other dimensions other than length, width, and depth. But just because we can't fully visualize them in our heads doesn't mean they don't exist. And we can use math to describe the ones we can't actually conceptualize. So you can keep going. You can add more and more dimensions. So if you sweep a cube back and forth in some other fourth dimension, then you would be in a fourth dimensional space. And so if you did that, if you did this to a cube, you would get what is known as a tesseract or a hypercube. And this GIF here is actually a hypercube in 3D rotating through that fourth dimension. There's a wonderful book, it's a relatively old book called Flatland. And the author talks about this whole world of pentagons and circles and squares living on a two-dimensional plane, and how life is and what laws are like there, how society works. And in one particular chapter, a sphere passes through their two-dimensional world. And of course, they can't see a sphere. A sphere is three-dimensional. So instead, what they see is a point appear, and that point slowly grows to be a circle, stops once it reaches the diameter of the sphere, and then shrinks again back to a point, and the sphere is done moving through their two-dimensional plane. Similarly, if a four-dimensional sphere, which is called a globe, were to pass through our three-dimensional space, we might see a tiny little ball grow in size to a full sphere, the diameter of that globe, that four-dimensional sphere, then shrink again back to the tiny little ball, disappear forever. So math can perfectly describe these different hyperspaces. So we don't have to stop at four-dimensional stuff. We can go 5, 6, 7 dimensions. I believe string theory, which is already sort of falling out of favor with some scientists, uses an 11-dimensional Calabi-Yau manifold. I don't know what any of those words mean, but you can see that we can do math with more than just our normal 3 dimensions. I bring up all of this because space-time is a 4-dimensional space where the 4 directions of motion are length, width, depth, and time. Now, time is not the 4th dimension, it just happens to be one of the 4. But there are 4 here. And we cannot, just like we can't picture what a hypercube looks like, we can't picture all 4 dimensions of space-time at once, but we can imagine. So in addition to occupying the 3 spatial dimensions of space-time that we ordinarily see, every object would also be stretched out through time. If you've ever seen the movie Interstellar, the very end of the movie, where it gets kind of trippy at the end, you screenshot here in the top right, it's actually a pretty good visualization of what traveling through 4 full dimensions, what seeing all dimensions of space-time would be like. Because objects that we see in our 3-dimensional space in our ordinary lives would appear as 4-dimensional things in space-time. And if we could see in 4 dimensions, we could look through time just as easily as we look to our left and our right. If we looked at a person, we could see every event in that person's life. If we wonder what really happened during, a historical event, what happened at the crucifixion, what happened at Stonehenge, at the building of the Great Pyramids of Giza, we can simply look at that object and know the answer. Now, in our ordinary lives, we only perceive those 3 physical dimensions of space-time, length, width, and depth. But remember, space-time is actually 4-dimensional. And so there's this really wonderful quote from a relatively famous textbook on general relativity that says, space is different for different observers. Time is different for different observers. Space-time is the same for everyone. And now space-time can have its own geometry. Just like we have geometry for 3- and 2-dimensional objects, space-time also has its own geometry. So to sort of get a handle on that, let's consider Earth's curved 2-dimensional surface. So because it's curved everywhere, there really is no such thing as a straight line on Earth. So for example, if you take a piece of string and lay it across a globe, if it's long enough, it will inevitably start to curve around the surface. So this leads us immediately to one fundamental difference between the rules of geometry on Earth's surface and the more familiar rules of geometry on flat surfaces that we learned about in middle and high school. The shortest distance between 2 points on a flat plane is always a straight line, but that cannot be true for something on the Earth's surface because there is no such thing as a straight line. So what rule gives us the shortest distance on Earth's surface? The shortest distance between 2 points on Earth's surface is a portion of a great circle, the circle whose center is at the center of the Earth. So, for example, the equator is a great circle, and any line of longitude those are the ones running north to south, are parts of a great circle. The lines of latitude are not great circles because their centers are not at the center of the Earth. So therefore, if you're seeking the shortest and straightest route between two cities, you must follow a great circle route. So if you wanted to travel the shortest distance between New York and Madrid, which lie about roughly the same latitude, you're not just going to follow that line of latitude. That's going to take you almost 6,000 nautical miles. That's the green line here in this figure. You want to take the portion of the Great Circle, the red line, which is about 200 nautical miles shorter. That's why if you ever look at flight paths of planes that are certainly going international, they do curve a bit. They're not just straight lines because it's not the shortest path. They'd be wasting fuel there. So similarly, we can talk about other types of spaces. So let's go over some rules of geometry real quick. In the flat geometry, the stuff that we've learned about in high school and in middle school, we know that parallel lines will always remain parallel. That the circumference of a circle is exactly 2 pi times the radius of that circle r. The straightest path is a straight line, and the sum of angles in a triangle will always be 180 degrees. You can draw any triangle you want on a sheet of paper. The sum of the angles will never be anything different than 180 degrees. However, in spherical geometry, like that of Earth is a sphere, parallel lines will eventually intersect. We know this intuitively. We know that the lines of longitude, the north-south lines, intersect at the North and South Pole, yet they are parallel. The circumference of a circle will be less than 2 pi r. The straightest possible path, as we just talked about, is part of a great circle. And the sum of angles in a triangle will always be greater than 180 degrees. There's also sort of saddle-shaped geometry, also called hyperbolic geometry, where here parallel lines will eventually diverge, moving further away from each other, where the circumference of a circle will be greater than 2 pi r. The straightest possible path is part of a hyperbola, and the sum of angles in a triangle will always be less than 180 degrees. So all this stuff was sort of figured out by the late 1800s by really smart mathematicians. The flat plane is called Euclidean geometry because a Greek mathematician called Euclid figured this out back in before the BC times. The spherical and the hyperbolic geometries are often called Riemannian geometries, I believe, because all the math was really worked out by one guy named Riemann in the late 1800s. So we know all this. But what does this, I can hear you saying, what does this have to do with general relativity with space-time? Well, because space-time, I apologize for that. Space-time has some geometry, and in reality, the actual geometry of the universe turns out to be a mixture of all 3 of these general types. So the Earth's surface, once again, is a good analogy. When we view only small portions of an Earth's surface, some regions obviously appear to be flat plains, but also Earth has some curved hills and valleys that are like the hyperbolic geometry, while of course the entire Earth is spherical. In a similar way, but in 2 more dimensions, the 4-dimensional space-time of the universe obeys different geometrical rules in different regions, but presumably has some overall shape. And the overall shape has to be one of those 3 geometries. Now, cosmologists can actually measure the overall shape of the universe by doing very careful experimental measurements of what is known as the density parameter omega, which is a sum of the density of matter in the universe, both normal and dark matter, and combine that with the density of dark energy in the universe. Current measurements place the density of matter to be about 0.3, the density of dark energy to be about 0.7. You can see I've plotted both of those quantities here, and the purple point is where our universe lies. So if you follow this line that we precariously sit on, we are right there on the spatially flat universe. So this means that the universe is likely infinite in extent. There's no edge, there's no center. Now, I do have to clarify that I mean the capital, sorry, excuse me, I mean capital U universe. Our observable universe obviously has a center. It's us. We are at the center of the observable universe, and it has an edge beyond which we can't see anything. But the universe beyond the observable universe is likely infinite and probably does not have a center at all. There's no edge to it either. You can also tell from this diagram, we'll get hints of some cosmology things we'll talk about later. You'll see these omega parameters, these density parameters again as well. But you can also see that this tells us that our universe is accelerating. We're above the accelerating, decelerating line, and it will be expanding forever. We're above the expanding forever, recollapsing line as well. So measuring these parameters tells us a lot about the geometry of the universe. So what are straight lines here then? So here the rules of geometry give us a way to determine the geometry of any localized region of space-time. In particular, we can learn the geometry of space-time by observing the paths of objects that are following the straightest possible path between 2 points. So for example, the straightest possible path is truly straight, then we know that space-time is flat in that region. If the straightest possible path is curved, then the shape of that curve must be telling us the shape of space-time. However, we can't actually visualize the time part of space-time nor the curvature of space-time. So how can we know whether an object is traveling on the straightest possible path? Well, Einstein used the equivalence principle to illustrate this. According to the equivalence principle, we can attribute a feeling of weight either to experiencing a force generated by acceleration, or to being in a gravitational field. Similarly, anytime we feel weightless, we can attribute to either being in free fall or traveling at a constant velocity away from any gravitational fields. So because traveling at a constant velocity means traveling in a straight line, Einstein reasoned that objects experiencing weightlessness for any reason must be traveling in a quote unquote straight line. That is, along a path that is the straightest possible path between 2 points in space-time. In other words, if you're floating freely, then your world line is following the straightest possible path through space-time. If you feel weight, then you are not on the straightest possible path. This actually gives us a remarkable way to examine the geometry of space-time. So remember that any orbit is an example of a free fall trajectory. So that means that the Earth's orbit and all the other planets, as well as say satellites around the Earth, the moon around the Earth, are all following the straightest possible path through the local space-time. It just happens to be in a slightly elliptical orbit. So this gives us a way to understand the curvature of space-time near massive objects. Now, what is gravity here? Newton's law of gravity claims that every mass exerts a gravitational attraction on every other mass, no matter how far away they are from each other. However, this idea of sort of action at a distance is pretty mysterious. So for example, how does the Earth feel the sun's attraction and know to orbit it? Newton was actually troubled with this himself. A few years after publishing his law of gravity, he remarked that one body may act upon another at a distance through a vacuum, and a force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has a competent faculty in thinking can ever fall into it. So basically saying anyone who isn't stupid should be worried about this. But no one came up with a better idea for 230 years. No one had a way to explain this mysterious action at a distance. That is, of course, until Einstein came along. Einstein's general theory of relativity removes this idea of action at a distance by stating that the Earth actually doesn't feel any force tugging on it in its orbit, and therefore will follow the straightest possible path through space-time. In other words, what we perceive as gravity arises from the curvature of space-time. So let's break this down a bit. We'll use an analogy that is used in every science special on the History Channel or the Science Channel or Discovery. And that is the rubber sheet analogy or trampoline analogy. So here, we're going to use a two-dimensional rubber sheet to picture space-time. And to make this analogy work, we're going to ignore friction, since of course there's no friction in space. So here we see a flat rubber sheet representing space-time in a region where it has flat geometry. Notice that the radial distances between the circles shown on the sheet are the same, and all of the circles have circumferences that follow the flat geometry formula of 2 pi r. Now, if you rolled a marble across this flat, frictionless sheet, it would roll in a straight line at a constant speed. This fact essentially illustrates Newton's first law of motion, which says that objects move at a constant velocity when they're not affected by gravity or any outside forces. Now, let's throw a heavy object like the sun into this sheet. So we'll represent with just a heavy mass, a heavy ball. This will cause the sheet to curve and form a bowl-like depression. So now the circles that were evenly spaced on the flat sheet are now more widely separated than near the bottom of the bowl, showing that gravity becomes stronger and the curvature of space-time becomes greater as we approach the sun's surface. So now if we rolled marbles on this rubber sheet, they could not go in straight lines because the sheet itself is curved. Instead, the marbles would follow the straightest possible paths given the curvature of the sheet. A particular marble's path would depend on the speed and the direction in which you rolled it, but you'll find that marbles rolled relatively slowly and close to the center would follow circular or elliptical orbits, while marbles rolled farther away or at higher speeds will follow parabolic or hyperbolic orbits. So by analogy, this tells us that depending on their speed and direction, planets or any other objects orbiting anything moving freely in space can follow circular, elliptical, parabolic, or hyperbolic orbits, which is exactly what Newton's law of gravity says they can do. However, the explanation for these orbits is different. Rather than orbiting because of mysterious force exerted on them by the distant sun, the planets orbit because they follow the straightest possible paths allowed by the space-time around them. The central mass of the sun is not grabbing them, communicating with them, or doing anything to them to influence them in any way. Instead, it is simply dictating the shape of space-time around it. So in other words, a mass like the sun causes space-time to curve, and the curvature of space-time determines the paths of freely moving masses like the planets. Now, I will say there are some problems with this rubber sheet analogy. This is supposed to represent the universe, but it makes no sense putting a mass like the sun upon the universe. Instead, we should think of the masses as being within the sheet. Plus, the rubber sheet only allows us to picture 2 of the full 3 spatial dimensions of space-time. But it doesn't show us the fact that the planets, so for example, it obviously shows us the shape of the orbits, and that some have more elliptical orbits than others, but orbits also have inclinations where they tilt above and below the sheet, so this doesn't show that. Plus, it also definitely doesn't show the time part. If this were, then the whole sheet would be rising above in the time direction, in that 4th dimensional direction, whatever that is. So there are some problems with this. Don't think that this is how scientists view the universe with this little rubber sheet. It's just a useful analogy to help us understand how gravity works in space-time. All right, following this through, we know that greater curvature of space-time means stronger gravity. And using this rubber sheet analogy tells us that there are 2 basic ways to increasing the strength of gravity. We either have to find a larger mass or increase an object's density. So finding a larger mass will cause greater curvature at any particular distance away from it. So for example, the sun curves space-time more than any planet, and the Earth curves space-time more than the moon. This is completely consistent with Newton's law of gravity, which says that increasing the mass of an object increases the gravitational attraction at all distances. Perfectly fine. The second way to increase the curvature of space-time is to leave an object's mass alone, but shrink it, increasing the object's density. So for example, we could compress the sun into a type of dead star called a white dwarf, which we'll talk about in a few weeks. And because its total mass would be the same, there'd be no effect to the planets. The Earth would continue along in its orbit, taking 1 year to complete an orbit around this new white dwarf sun, although The lower amount of light and heat being emitted from a white dwarf would certainly cause problems for the life living on Earth's surface, but the Earth itself would be fine. But space-time would be much more curved near the compressed sun's surface, reflecting the fact that gravity is much stronger on the surface of a white dwarf than on an object like the sun. Again, the idea that surface gravity on an object of a particular mass grows stronger as the object shrinks in radius, completely in line with Newton's laws. But now let's imagine that we keep compressing the sun to smaller and smaller sizes. Now, far from the sun, once again, nothing would be happening. But near the sun's surface, space-time would become increasingly curved as we shrink the sun in size. In fact, if we shrink the sun enough, we'd eventually curve space-time so much that it, in essence, would become a bottomless pit. And we know these bottomless pits by the name black holes. So a black hole is essentially a place where space-time is so curved that nothing that falls into it can ever escape. And the boundary that marks that point of no return is the event horizon, because events that happen within its limits can have no influence on our observable universe. Now, black holes do not arise in a universe that's purely governed by Newton's laws. Newton never thought they existed. And in fact, these were so weird that most physicists and astronomers did not think they existed, just thought this was a mathematical curiosity of general relativity. But of course, now we have tons and tons of experimental evidence, as well as at least one pretty cool picture of black holes. So we are pretty sure they exist. All right. So now let's look at how gravity affects time. So once again, here's another thought experiment. Let's imagine that you and Al are floating weightlessly at opposite ends of a spaceship. You both have watches that flash brightly each second, which you synchronized before you got on the spaceship. And because you are both floating freely with no relative motion between you, you are both in the same reference frame. Therefore, you will each see each other's watches flashing at the same rate. But now let's suppose you fire the spaceship engines. You put your foot on the gas pedal and we start accelerating the spaceship with you at the front and Al at the back. So now, when the ship begins accelerating, you and Al will no longer be weightless. And this acceleration will introduce a change to the situation, which we can understand by imagining or watching this as some outside observer outside the spaceship. So remember that observers moving at different relative speeds are in different reference frames. So when the ship is accelerating, its speed is constantly increasing relative to the outside observer, which means that both you and Al are constantly changing reference frames. Moreover, the flashes from your watches take a bit of time to travel the length of the spaceship. By the time a particular flash from Al's watch reaches you, or a flash from your watch reaches Al, both your reference frames are different from what they were at the time the flash was emitted. So yeah, that's all just what I just said. Now, if you're a fan of sci-fi, you will no doubt be aware of what's going to happen in this scenario. Peter Capaldi's last episode as the Doctor in Doctor Who dealt exactly with the scenario like this. Okay, so because you are at the front of the accelerating spaceship, your changing reference frames are always carrying you away from the point at which each of Al's flashes is emitted. Therefore, the light from each of his flashes will take a little longer to reach you than it would if the ship were not accelerating. So as a result, you will see Al's flashes, instead of seeing them 1 second apart, you'll see them coming a little more than 1 second apart. You'll therefore conclude that time is running more slowly at the back end of the spaceship. Now, of course, we always want to know what Al thinks. So from Al's point of view at the back, his changing reference frames are always carrying him towards your flashes. So they will take a little less time to reach him. And so he'll see your flashes coming a little less than 1 second apart. He will therefore conclude that time is running fast at the front end of the spaceship. And the greater the acceleration of the spaceship, the greater the difference in the rate at which time passes at the two ends of the spaceship. So now let's use Einstein's trick of applying the equivalence principle. If we do that, then we see that the exact same thing will happen for a spaceship at rest on a planet. Time will be running more slowly at the bottom than at the top. Now, obviously, we don't just have spaceships lying around here, unless you're Jeff Bezos or Elon Musk. Instead, we got mountains and plains. This happens between someone at the bottom of the mountain and someone at the top of the mountain, and someone on the ground and someone in a plane. So, for instance, on a flight from Cleveland to Atlanta, which takes about an hour and 47 minutes on average, whenever I take that trip home, I will actually be 0.0000045 seconds younger than the people on the ground. And when Scott Kelly, the twins Scott and Mark Kelly, whom one of them is a senator now, Scott Kelly stayed on the International Space Station for a full year. While Mark Kelly, his twin, stayed on the ground. Thanks to this gravitational time dilation, Scott Kelly was a full 0.05 seconds younger than his twin after all this was said and done. And so the stronger gravity, hence the greater curvature of space-time, the greater the effect of gravitational time dilation. Now, this is barely noticeable on a planet with as weak gravity as Earth's. But when we're talking about black holes, like in the movie Interstellar or around white dwarfs, then this really does have a huge, huge effect. Now, don't take my word for all of these things about general relativity. We obviously want to experimentally verify them because, as a very wise person once said, logic only enables you to be wrong with authority. So we need experimental tests. One of the first tests that we ever did on general relativity was using Mercury's orbit. So Newton's law of gravity predict that Mercury's orbit should precess slowly around the sun because of the gravitational influence of the other planets. You can see here in this image, it's the actual elliptical orbit itself will move around the sun. And careful observations should show that it does indeed precess, but careful calculations made with Newton's law of gravity cannot completely account for the observed precession. And this discrepancy was small. So Urbain Le Verrier, French mathematician, noted in 1859 that Mercury's observed precession couldn't be completely explained by Newton. Now, this brings you into the history of planetary searches in the late 1800s. They had just found Uranus and Neptune. They found Neptune with math. So they figured, hey, maybe we can find a planet between the sun and Mercury with math as well. They went ahead and named it. They named it Vulcan. And they searched and searched and searched, but they never found it. There is no planet Vulcan between Mercury and the sun. And this effect of the observed precession of Mercury and the calculated precession of Mercury not matching up went sort of unexplained. That is, of course, as I'm sure you probably guessed, that is until Einstein. So Newton's law predicted that Mercury should precess by 5,557 arc seconds per century. An observation showed a precession of 5,600 arc seconds per century. And Einstein showed in 1915, in November of 1915, that his theory of general relativity recovered the missing 43 arc seconds per century. He was actually so excited about this result that he was unable to work for the next 3 days. He later called this moment of his success the high point of his scientific life. This is a relatively simple calculation. You do it in any general relativity class. One of the first problems you're assigned as homework. In fact, I was assigned this problem as homework. I didn't get it right, so it's not that easy, but it is well understood now and completely explains that observed discrepancy. Another very well-known method of testing general relativity is through gravitational lensing. So since light always travels at the same speed, it will always follow the straightest possible path. If space itself is curved, then light paths will curve as well. So we could propose the experiment of, let's say at night, we measure an angular separation between two stars. And during the day, as the sun nears one of the stars, because space-time is more drastically curved near the sun, light should be curved from the star that appears closest to the sun, which will make us think that it's actually moved closer to the other star on the sky. Now, obviously, you don't want to stare directly at the sun to do this experiment, so you've got to wait for a total solar eclipse. And so that's exactly what they did. They waited for a total solar eclipse. Tons and tons of physicists and astronomers descended on Brazil in 1919. and I'm sure they had fun for many reasons, and did these observations, and it matched Einstein's predictions exactly. And this is what really catapulted Einstein into being a celebrity, was this exact matching. Now we could do this, we could see gravitational lensing, not just with the sun, but with tons of other things. So here I've got some very beautiful pictures where some even more dramatic effects happen when there's a distant star or a galaxy that lies behind another object with a strong gravitational field. So on the left here, we have the phenomenon known as the Einstein cross, where this faint kind of fuzzy thing in the middle here, that is a foreground, I believe, galaxy. I'm unsure. You can go look this up. It's got a Wikipedia article. Just search Einstein cross, and it'll tell you. But then these 4 points of light are not 4 distinct objects. That is one object, and its light is being bent around this foreground galaxy in 4 different directions. It's very cool. In the middle, we have what is known as the smiley face, where the 2 eyes of the smiley face are 2 foreground galaxies in this galaxy cluster. And these really weird, wonky, curved shapes, that is one galaxy. As light is being bent around the 2 foreground galaxies to give us these really curved, weird, bluer shapes. And in fact, on the right is a GIF of a black hole, a simulated image of a black hole moving in front of the Milky Way. You can see gravitational lensing. So you may have seen it in the movie Interstellar as well. They did an excellent job. That's what happens when you get Nobel Prize laureate Kip Thorne to be your scientific advisor on set. You get all the science really right. So all this is very, very cool. In fact, this is very, very useful for studying the early universe. So here's a beautiful galaxy cluster, Abell 2744, taken with the Hubble Space Telescope. You can see a bunch of different galaxies, nearly everywhere where you see a really weird, wonky shape. So there's a curved shape, here's some curved shapes, really weird curved shapes here. Those are all gravitationally lensed background galaxies. But if you do some really deep looking, and they've done it on these boxes labeled A, B, and C, which you see the insets here, pointing these really weird red fuzzy objects, those are galaxies in the very early universe that are just being formed. And so thanks to gravitational lensing, we can get an idea about how galaxies look like and behaved and were formed when the universe was very, very young. In fact, I once attended a presentation at Case Western where astronomers were using gravitational lensing of galaxies, of these very far away galaxies, to detect supernovae. Because if a galaxy was lensed in multiple images, then you would see a supernova appear in one of the images, and then you could just wait maybe a few months, maybe a few years, and the supernova would appear in the other image. It's very, very cool. It allows astronomers to do some really, really cool science. And it's all thanks to general relativity, the fact that the universe works like this. Just like last week we talked about time dilation, general relativity also has a version of that. Where once again, we are looking at, things move slower at the bottom than at the top of a spaceship. And some very, very accurate experiments, the National Institute of Standards and Technology here in the United States measured this gravitational time dilation over just a distance of a meter. You've got to have some really accurate measurement tools to get that measured. GPS satellites take into account gravitational time dilation when reporting where to go for drivers. Otherwise, people will be driving into lakes and brick walls all the time. You can also imagine that suppose that in a lab on Earth, you've got a particular gas that emits a spectral line with a frequency of 500 trillion cycles per second. So general relativity claims that time is running more slowly on the sun because it has more mass. So the sun has this gas, it will emit that spectral line more slowly than 500 trillion cycles per second. And this is called gravitational redshift. And we measured it for spectral lines on the sun and many other stars, exactly matching the predictions from the theory. Now, I do want to say this gravitational redshift is a completely separate phenomenon from the Doppler effect, the Doppler redshift we've already talked about, and from the cosmological redshift that we will talk about in a few weeks. I'll mention that again when we get there. but it's 3 different redshifts happening here. They're not all the same thing. And of course, a very good prediction of general relativity is that any sudden change in the curvature of space-time should propagate outward like ripples in a pond. And these ripples are the now well-known phenomenon of gravitational waves. Now, when the book that I'm using to get all these ideas out of was published, they hadn't yet discovered gravitational waves. But of course, now we have. So this GIF on the left are the ripples of space-time. Of course, once again, just an analogy because you can't see all 4 dimensions at once. But the ripples of space-time caused by a binary neutron star system, 2 very dense stars orbiting each other very closely. And then this next little video I'll play is the sound of 2 black holes merging, first detection of that from LIGO. What will happen in this clip is it will play twice at the normal frequency. It'll be a very deep tone, which you may not be able to hear. Then it'll play twice at a higher frequency, which accentuates the chirp of the black holes merging. And then we'll repeat those 4 things again. I will say, and I'll put it in the description down below, there's a lovely website that does like the sounds of gravitational waves that you go play around with and learn how these sounds are created. So I'll shut up if you want to boost your audio to hear it. Let's see if you can hear it. All right. So finally, if you've ever seen any sci-fi thing, Star Wars, Star Trek, Doctor Who, whatever, you're no doubt aware of the concepts of hyperspace, wormholes, and the warp drive. So last week, we talked about using special relativity to cut down the time it takes to travel to the nearby star Vega. But let's imagine even at 25 years, even the 1 year to travel near the speed of light is too long. So let's see if we can shorten that time just a bit. What if Vega and Earth are closer together than they are here in our 4-dimensional space-time? They're close together in a multidimensional hyperspace. Then maybe there's a tunnel through that hyperspace, which we, of course, call a wormhole. Now, no part of this violates relativity. No part of it actually violates any of the laws of physics, since at no point would you be traveling faster than the speed of light. You're just taking a shortcut. Just like if you want to travel through Atlanta, instead of getting on I-285 and taking the perimeter, you're not breaking the law by going through I-20 and getting on 85 or taking back roads. You're not breaking any laws there, just taking a shortcut. So this doesn't, wormholes in hyperspace and the warp drive even don't really violate any laws of physics. Yet many people, many physicists and astronomers think that wormholes don't really exist. Because wormholes seem to make time travel possible. And unlike the paradoxes that we dealt with last week, time paradoxes don't have an easy resolution to them. So in the words of physicist Stephen Hawking, time travel is probably prohibited by the universe to keep the world safe for historians. Otherwise, it gets very, very complicated real fast. So I'll end on this slide, but let me say some ending words here about what we've learned over these past 2 weeks. So in our daily lives, space and time seem separate and distinct. And for most of human history, people simply assumed that this appearance must reflect reality. Thanks to Einstein, we now know otherwise. Space and time are intertwined in ways that earlier generations never even began to consider. As Hermann Minkowski said in 1908, henceforth, space by itself and time by itself are doomed to fade away to mere shadows, and only a kind of union of the two will preserve an independent reality. In the more than 100 years since Einstein first published his special theory of relativity, both the special and the general theory have been subjected to extensive and precise testing. So far, both theories have passed every test. While it remains possible that future tests will force modifications to the theories of relativity, it seems inconceivable that new discoveries could change their underlying message about the intertwined nature of space-time, with its implications for our understanding of everything from the passage of time to black holes to the overall geometry of the universe. The astonishing transformation that relativity brings to our view of space and time has also caused philosophers to debate its implications for concepts such as fate and free will. These debates are fascinating and well worth exploring, but remember that they do not affect the data from which the scientific theories are built. In other words, while there are many different viewpoints on the philosophical implications of relativity, only the scientific aspects of the theory are confirmed by data. With that in mind, let's turn to Einstein himself for our last word on relativity. Here's what he said about a month before his death on April 18, 1955. Death signifies nothing. The distinction between past, present, and future is only a stubbornly persistent illusion. So that's the end of our little duology here on relativity. Next week, we'll go from the large scale, talk about the small scale stuff, particles, quantum mechanics, the building blocks of the universe, and then we'll talk about stars, galaxies, and the universe at large. So with that, I wish you all a good night or good whatever time it is when you're watching this. Leave a comment below, like, subscribe, and I will see you next week.